Hi, this is Mrs. Rutchling. Welcome to Chapter 17, Buffers. A buffer will resist a pH change even if you add an acid or a base. It consists of a weak acid and its conjugate base, or its salt. That's the most common kind, but you can also have a weak base and its salt, the conjugate acid. Looking at plain water, the pH for water is 7. If I add 0.01 moles of hydroxide, I get a pH, and here's the calculation, of around 12. If I add 0.01 moles of acid, I get a pH about 2. However, if I do the same for a buffer, notice the pH changes are very small. What's happening? If I have a weak acid and its conjugate base, if I add hydroxide, the weak acid is going to react with it to create the anion in water. If in this same solution I would add acid, it reacts with the anion and creates the weak acid. I can have the opposite if I have a weak base and its conjugate acid. The conjugate acid will react with hydroxide to produce the weak base in water. The weak base will react with the hydrogen ion to create the conjugate acid. A very common buffer is acetic acid and the acetate ion. Usually sodium acetate is used. If I have this buffer and I add hydroxide, the hydroxide is going to react with the acetic acid to produce more of the acetate ion. If I add acid, it's going to react with the acetate ion and create more of the acetic acid. Let's try to solve this problem using our ice chart. We have acetic acid and sodium acetate. If we look at what is in solution, we have acetic acid, a weak acid, so we know that's going to affect the pH. Sodium is not going to affect the pH, but the acetate will affect the pH. Water is negligible if we look at our acid constant here. Putting these values into our ice chart, then we can use our equilibrium constant, our equilibrium expression, and plug in those values. Make the assumption that the change will be less than 0.5% of 0.5 molar. Gives us our hydrogen ion concentration. And if we take the negative log of that, we get our pH of 4.7 since we only have 1 sig fig in our molarity. When you do buffer calculations, and this equation that we're going to derive is only good for buffer calculations. The first thing we want to do is create the equilibrium constant for the dissociation of just this general HA acid. Rearranging it to isolate the concentration of hydronium ion, we get this equation. If we take the negative log of both sides, this should look familiar to you. The negative log of the hydronium ion is pH. The negative log of the equilibrium constant is the pKa. We've also used our log rules here to separate these. Once we've taken the negative log and converted that to the pH and pKa, we still have this negative log of the concentration of the acid over the anion. Rearranging this by taking the reciprocal, and that makes it a positive. This is the Henderson-Hasselbalch equation. It's very useful for calculating the pH when you know the concentration and the change is negligible, so it's a buffer. This equation is on the equation sheet. It has been on there in the past, it has been taken off, but this year it will be back on, so it is fair game for you to use it. If the pH is equal to the pKa, we have a good mixture of protonated and deprotonated forms. When you're talking about the protonated form, you're talking about the acid, so the concentration of the acid is greater than the concentration of the anion if the pH is smaller than the pKa. If the pH is greater than the pKa, then the anion form is dominant, or higher concentration. Pause the video and give this one a try. You may use the ice chart and plug it in, or you may use the Henderson-Hasselbalch. Looking at the species that are present, we have the acid, sodium, which we don't have to worry about, the anion, and water. Seeing the Ka means we can eliminate water. We don't have to worry about that. And so we just have the acid and its conjugate base. We can plug in, this would be our results from our ice chart, or we can use the Henderson-Hasselbalch. Either way, we should get close to the same answer. Analyzing the buffer, you want to look at its capacity. How much of the acid or a base can it absorb before there's a significant change? Two things that increase the capacity, the concentrations of the acid and its conjugate base. If the ratio is 1, if the amounts are equal, then it can react with either the hydrogen ion or the hydroxide ion. If there's large concentrations of the acid in this conjugate base, then it can react with a larger amount of hydrogen ion or hydroxide. When you're designing a buffer, you look for a pH, and the pKa of your weak acid should be approximately plus or minus 1. Buffer A has acetic acid and sodium acetate. Buffer B does as well. The volumes are the same. The difference is the concentrations. Since the concentrations are equal, if we plug those in, the hydrogen ion concentration will be close to the Ka. They're both going to have a similar hydrogen ion concentration. What will make the difference in these buffers is the difference in concentration. Buffer A will have a higher buffer capacity because it has a greater number of moles to react with the acid or base that is added. The greater those amounts, the more that it can react with an acid or a base. We need a solution, and we want it to buffer at pH 4.30. These are the acids, and we would use their corresponding sodium salts. Which one would be more appropriate? If we look at the pKa, we would have a pKa of 2.87, 4.87, 4.19, and 7.43. Looking at the closest pKa, the benzoic acid would create the best buffer. Is there a way to estimate these? Yes. You can get a general sense. You can at least eliminate some answers. 1 times 10 to the negative second is 0.01. 1 times 10 to the negative third is 0.001. Our value for the first pKa is 1.35 times 10 to the negative third, 0.00135. So it falls in between these two. If I take the negative log of 0.01 is 2, the negative log of 0.001 is 3. My value is going to fall between there, so I can look for the answer that is between 2 and 3.